All right, let's look at a couple of common osmotic pressure or osmotic concentration problems. They're dependent, just like the freezing point depression and the boiling point elevation, on the number of moles of particles in solution, and that's referred to osmolarity. So here's a simple equation for that. This would be the number of moles divided by volume, or another way is to say it's the molarity times I, and this I is the same one as we looked at in freezing point and boiling point changes. So here you have this I. So let's look at this right here and apply it to this situation down here. So here you have that concentration, and you're asked to know what the osmolarity is. So this is a way of reporting a concentration that is going to be directly proportional to the osmotic properties of the solution. So in this case, we've got the molarity, and it's times then this I. So the I is the number of actual particles in solution that comes from this molarity of solution. So let's look at this. We have potassium sulfate. That's K2SO4. Remember, sulfate is a -2 anion. Potassium is a +1 cation. So this is the formula right here. That means when 1 mole of that goes into solution, we have then 2 potassium cations and 1 sulfate anion. 2 minus. So that means for every mole of this that goes into solution, we actually get 3 moles, 2 of the potassium cation, 1 of the sodium sulfate anion that goes into solution. So if we were applying that, we would have 0.1 molar of the solution times 3, because we have then 3 particles come from 1 mole of this, and so we'd get an osmolarity of 0.3. This one is a little bit different. We still want to know the osmolarity, but here we have a mass volume, and so if we say that's really a 0.9% mass volume, so that would be that many grams, 0.9 grams, in 100 milliliters of solution. And so if we were doing that, if we took it to liters, we'd multiply by 10, and we'd have 9 grams in 1 liter. Let's see, let's fix this up a little bit more here. So we'd have 9 grams of sodium chloride in 1 liter of solution. We'd have to convert that now to moles. And so we would have then 1 mole of sodium chloride is 58.5 grams. And so if we multiplied by that, that's going to get rid of our grams. And we're going to have then that many moles. So this is going to be our moles per liter. And so that's our molarity is going to be 9.0 over 5. 8.5, and so these are this would be that molarity, and so that looks like it's about 1/6, something like that. But again, if we come back with the I factor right here is if we take 1 mole of so in that case, let's see, we'll get it right. 1 molar solution of sodium chloride. So when that is in solution, we have 1 mole of that, but we have then, in terms of particles, we have 1 mole of sodium cations and 1 mole of chloride anions. So this would be all times 2, and so we would get that right there for the osmolality of it. So finally, let's look at this equation for the osmotic pressure. The key here then is to realize that this is really like the ideal gas law. It's got a little bit different right there with that I value, but we've talked a lot about what that I value means. This is the ideal gas constant. And again, anytime you do anything like that, that temperature has to be in Kelvin. So this is the osmotic pressure. So if we set this one up, we'd have then the osmotic pressure is equal to our N, and in this case, it's N over V is actually molarity, because it's what? Moles over volume, and that's what molarity is. So we would have one, so our N over V, if we did it like that, times I RT is equal to what? 1 molar, which is that right there. Our I value then, in this case, is 2, and so we could then easily say that is 2, and then the T, we would have to come in and say the T right here would be, if it's 25 degrees, that's K is 298 K, and so we would end up then with this overall equation. So pi is equal to 1 molar times 2, the I is 2, the ideal gas law, and then 298 K. And so that should give us what we need. We can break this down into its component units. So that 1 molar would be 1 mole over 1 liter. And so now we have everything we need.